Okay.
Okay, yeah, let's start.
So let's see. I guess I didn't solve really the easier problems, so I guess we'll be going a little bit in the deep end. Let's see.
So which one? Yeah,
I think this one would be the easiest one I saw.
Yeah, this one, yeah, probably the second easiest one, but it's pretty.
So let's see. So in this problem, there are n bathroom stalls. So like there's n stalls, and so there are n stalls and there are m people who need to use them, and each person either requires toilet paper or doesn't, and there's only one roll of toilet paper because of shortages. So they can only, so each person takes 1 unit of time to go, and you can only have one person who needs toilet paper at a time. So the problem is each person has a deadline for when they need to be done, and the question is, can you satisfy everyone's deadline? So if toilet paper was not part of the problem, then there's a clear greedy solution where you should like always fill up the stalls with the people who need to go first. So like you sort everyone by deadline and then fill up the stalls, and then check that each person enters the stall like before their deadline. So how do we handle the issue with toilet paper? So my solution isn't actually constructive. I don't like find a solution, but instead what I do is I find several conditions that would make it impossible, and I just check if each of them can happen. So so we still sort people by deadlines. So like let's say I have people 1 to up to m, and I check for each prefix of these people, I check ignoring toilet paper, can they all be done before the deadline? So in other words, it would be like number of stalls times the time would be less than or equal to, or number of stalls times time would be at least the number of people. So I do the one check. So like I check that there's enough time to satisfy all people. And then I check that there's enough time. Wait, let's see. How do I say this? I should say like number of people is at most like the max deadline of those of that prefix of people times number of stalls. And I also check that number of people who require toilet paper is at most the deadline. So my solution isn't actually constructive, but I like check these conditions which are necessary for there to be a solution, and we don't actually need to construct one. We just say yes or no.
What's the second thing you're checking?
So like if there are like for example, if there are in the first I people sorted by deadline, there are all their deadlines are at most a certain time, and there are too many people to like satisfy that deadline.
Okay.
So yeah, I just like make these two different checks, and then I kind of hope that they're sufficient. And I think the constructive solution is to sort of I think they said like in the meeting that
I didn't code it, but I thought about this during the context. So what I would do is I will first handle the toilet paper people and sort them, and then going backwards, and then just so basically I want to place those people as late as possible, but if it's already taken, then they need to be moved forward. And after those is done, then it's just greedy for the rest of the people.
So the solution is put the people who require toilet paper like as late as possible.
Yeah.
And then then fill everyone else up in the usual greedy way. Okay.
Yeah.
That makes sense. So that's H. Next is E. So this problem maybe looks complicated, but it's actually quite simple what they're asking you to do. So the problem is that there's like this specific way to encrypt a string, and all you have to do is just follow those instructions, basically. So the way a string is encrypted is by imagining the characters as numbers mod 37. So like each character, it tells you how it's mapped to a number between 0 and 36. And then what we do is we split it into substrings of length n, and we have a bunch of like vectors. And if it's not a multiple of n, then you pad it with spaces. So like 36. And then they also give you this matrix, and then what you're supposed to do is multiply the matrix by each of these vectors. So when you multiply it, you get another vector. And then you just convert each vector back to the characters, like the opposite of what they said. But yeah, I don't really know if there's much to say, you have to just follow the instructions, kind of.
Yeah.
I guess there's spaces, so you need to use like get line instead of just reading in a string the usual way. But yeah, you can just like make a couple functions for converting characters to and from integers mod 37. And then if you just use matrix multiplication and take mod 37, it's just like follow the instructions, kind of.
Yep.
So then part 2 is harder, but it's also kind of straightforward. So they ask you to do the exact opposite of problem E, where we have we know a string and we know what it encrypts to, and the question is, what's the encryption matrix that is consistent with this? And these numbers have to be between 0 and 36. And if there's a unique solution, we should find it. If there's more than one solution, we should say that. And if there's no solution, we should say that. So for this problem, there are a couple of things to observe. One is that 37 is a prime, and that's actually important. So like this means that integers mod 37 are a field. If you don't know what that means, that's okay. What that basically means is that the numbers have inverses. So like, so 1, 2, 3, or some, etc. to 36. Each number here has a different number, or possibly the same, between 1 and 36, where you can multiply it and you get back to 1 mod 37. So let's look at what the structure is. So like, let's say we have this matrix that we don't know. These are all unknown variables. Let's see, AN1. So like we have a bunch of variables here, and we want to think, what are the constraints in the input? So like the string is, it gives us this string, which we should break into blocks of n. So let's say like we're considering one block. So like we know that if we multiply by this vector, then we should get this other vector. So S and T are known, but these A values are not known. So what we actually get here is that so A for like, so this equality means that each row has equality. So we should say like for each row I, we have like AI1 S1 plus AINSN equals TN. It's like we have a bunch of equalities here. And so the SI are known, the TI are known. I should say TI. So those are known, but the A's are not known. So this is actually a linear equation, mod 37. And these are the variables we need to solve for in the system of equations. So it's like in summary, like what the actual problem is it's like we have a system with n squared unknowns. And how many equations are there? That would be the length of the string. Let's see, did we even say what the length of the string is?
I guess you just read it in and then you know. So.
Yeah, I'll just say m equations. So m is the length of the string. So so you can solve a system of linear equations with Gaussian elimination. And the property that 37 is prime is important for this to work. Otherwise it won't, and you should do something else. So what this will tell you is that it will tell you exactly what they ask for, like what's the solution. It will tell you how many solutions, including if there's no solution. And so your template, like if you have a good template, then you should be able to find this in there. It might not be mod prime, it might be like with real numbers or like with, or just mod 2. But it's pretty similar and you can adapt it. Yeah, I guess this is one of the harder problems, but it's also like, it's straightforward if you know this background.
I think this is a kind of ECNA flavor. There's often this kind of solving system of equation problem.
Mm-hmm. So should we move on?
Sure. So I guess other than Gaussian elimination, I guess the other is computing inverse of matrix. That's
well, the best,
harder to code, or I don't know any. Yeah.
The best algorithm for matrix inversion is just elimination, really. So
okay.
It's actually like it's just like a slower elimination.
Mm-hmm. So did you use the library, the code from the what's the KTH, or did you?
Yeah, I used that. I didn't see that they had mod 37 or like mod prime, but I adapted their code for like real values. Okay.
Yeah, so just one more. So this modular arithmetic model prime number is very much similar to just standard arithmetic, like with a rational number or real number.
Mm-hmm. Yeah, it's good to know model arithmetic. Okay, so let's move on to problem I. So here we have like this map of walkways. So we have a bunch of like line segments that are walkways. And there are 2 people. So there's a person S and there's a person F. So person F just walks like in a straight line segment until a certain point. And then person S, you know their initial position, and they are restricted to walking only on the walkways. Both people, like their walking speeds. And the question is, can person S move along the walkway and meet person F at a point? So person S has to reach there like at the same time or earlier as F. And you have to find like the earliest possible time. So like, for example, it might be that person S can walk over here, but it's too slow, but they can walk over here and it's fast enough. And maybe they can also walk here, but this is the first time, so you should choose it. So the constraints are like, there are 500 lines, so we can't, we have to be a little bit careful, but it's still relatively low. But yeah, so let's see. So one thing we can do is for each pair of line segments, because there's only 500 of them, we can check, do they intersect? And if they do, what's the intersection point? So that's one thing we can afford to do, like compute all of the intersection points, including where F intersects the segments. So like we can identify all of these interesting points. Let's also include like S and F as points. And like F finish. I guess they call it F1 and F2. So we can identify all of these interesting points, but now how do we think about this? So if we want to check if a certain point like S can reach it before F, we should check it with the shortest time to get there, or in other words, like the shortest distance. So this is like a shortest path problem. And for that, you can use Dijkstra, assuming that you have like this graph built. So really the challenging part is to actually build this graph, and how much time does it take? So I believe you can, I guess like one easy thing to do would be to say like for each line segment, you could say for each of the points that intersect that, like all the interesting points on the line segment, you could connect each pair of them with the distance. But then you would have like n squared edges for each line segment. So this would actually make the whole graph have about like n cubed. And that might pass, but I'm not entirely confident in it. Because like there's only 1 second. And it's a lot of like floating point stuff. But what you can do is instead of connecting each pair for each like two points on a line segment, if they're adjacent, you should connect them. And how you can identify if they're adjacent is by sorting them on the line. So like, say like you have a line segment with points A and B. Given some point P on the line segment, we can give it the number P minus A dot B minus A. And if we sort all the points by this value, then they'll be like in the correct order, so you can connect adjacent ones. So like this process will give you about n squared points and about n squared edges. So the time complexity will be like n squared log n. So yeah, there are some concerns about epsilon, like since there's floating points, you should like think about those things. Another issue, this was the bug I had, which was like the path of F. I wanted to treat that like any other line segment, but it can actually run into a bug. For example, if I was treating this no different than a walkway, which can be a problem if like person S can reach this intersection point, but person S travels faster than F and then can catch up to person F. And then it would like identify a false time that they can meet. So that's like, that's a bug that's easy to run into.
So how did you find out the bug?
Well, I spent a lot of time looking for other things, but then eventually I guess that it's probably something else. It's probably something logical in my code because like several people solved it in like one submission. So So I assume that it's not just like some really bad floating point stuff.
Some weirdness. Mhm.
But yeah. That's the kind of scary thing about geometry, where like they get really complicated statements and the implementation is complicated, and it's hard to tell what's the problem. Like, is it your thinking? Is it just the implementation, or it's hard to tell. I guess next is problem L. So in this problem, we have several apartments, gates, and stations. So each worker is in an apartment and then needs to go to a station. And it doesn't matter which station they go to, but each worker should be like in exactly one station. And there's also a constraint that like each gate has an A and a B. There's two different gates. So a worker should, or you can't have two workers go to the same gate. And also you can't have two workers go to like adjacent positions. It's like if two workers are in adjacent gates, then they can't be like touching. So like I can't have a worker in this B and also in this A. So
I didn't read the problem. So each apartment has one worker?
yeah.
Okay.
It's like there are n workers.
And then they only go to the either A or B in the same level as that worker, or they can go to.
So for example, like
so that each worker has two choices.
Each worker has a choice of like the A or a B. They can go to like there's no restriction on which gate they can go to or like which station. The constraint is that they have to like be separated enough. So two workers cannot go to the same gate, and two workers cannot go to adjacent gates where the top one is at a B and the lower one is at an A.
So basically, if you view these gates as a linear array, just nothing can be adjacent.
So we can just imagine it like there's two n spots here. And we can't have two workers in adjacent ones.
So then what's the station's significance in this problem? So after
so all the n workers have to go to all the n stations.
So each worker go to one station?
Each worker goes to one station.
Okay.
And
any other constraint?
Yeah, the other constraint is we want to find the minimum total distance that the workers walk. And what we know is for each worker, what's the distance to all of the gates? And we also know the distance from all of the gates to all of the stations.
I see.
It's like we have this like complete bipartite. We have like these two complete bipartite graphs.
I see.
And we know the distances for each edge. So yeah, the question is, what's the minimum total cost? And the constraint is like pretty small, it's like 50. So some background would be, what if there's just n workers and n stations and we completely forget about gates? Like what if we just have this situation where we have to assign workers to stations and there's no gate constraint? This is called the assignment problem. It's also commonly formulated like there are n people and there are n jobs, and we want to, each person has like a cost or an amount of profit to like be assigned to a job, and we want to like minimize cost or maximize profit. It could go in like two different ways. The solution is like, there's something called like the Hungarian algorithm. But more generally, there's like min cost max flow. So that will give like an n cubed algorithm to this problem if there are n people. So like if we just wanted to So like, I don't know, there's a lot of background behind this, but like, if you have a bipartite graph, then like you can find if there exists a perfect matching, like if some edges are gone, using flow, by like adding a source and a sink. So like the max flow in this graph will give you the matching by looking at like which edges here have flow going through them. So min cost max flow is more general, where each edge has a cost and you want to know the minimum total cost. So like sending flow through an edge costs something, like for each unit of flow through it. So in this case, we can like make all of these costs 0 and make all of these costs like whatever the distance is. And then it's like equivalent to the problem I described. So for this problem, it can be solved like if we have that specific simpler problem, then the solution is n cubed. But we do not have that problem. We have these gates. So how do we deal with the gates? I was actually struggling for this a bit. But then I realized like it's not an accident that there's exactly 2 n gates. So there's only so many ways you can choose some of these so that no 2 are adjacent, and you choose like n of them. How it actually works is that some prefix of the gates have the worker going to the A gate, and some suffix of them have the worker going to the B gate. So if we know like which gates they go to, then it actually reduces to the problem I described earlier, where workers are only allowed to go to these gates, and then they can only go from these gates to the stations. And it's just like 2 instances of the problem I described. So essentially what the solution is we check where should the splitting point be. We try all possible ones. So there's like n+1 possible splits. And then we say we have to use the A gates up here, and we have to use the B gates down here. So we do like that n cubed solution, n+1 times. So the complexity overall would be like n to the 4.
Okay.
So, yeah.
Yeah, I don't know whether I remember ECNA traditionally have the property that the line of code for all the problem will be fairly long, and I think this time at least the descriptions are all also very long.
Yeah.
It's really hard to actually to read all of them.
Yeah.
Cool.
I don't know. In this problem, I thought the observation about splitting points was kind of cool, but yeah. I thought the stuff after it is extremely obvious if you have the background, and then extremely like you're like completely lost if you do not know the background. Like you have no chance of solving it if you haven't seen this stuff. So mixed feelings for me.
Yeah, but I guess having one flow problem is normal. So
I guess that's all the problems I solved. Richard isn't here to explain the problems he solved, or is he?
Is he? Let me see.
I think he's not here.
He's not, yeah. So it's okay. I think maybe Trung can explain.
I think I read the problems. Let's see.
Oh yeah, this one. This one I can. Yeah, those are the easy ones. Yeah, I can talk about them. So.
I think I read them.
This one is
I
actually trivial.
don't know how to solve. I actually don't know how to solve this. For problem G, it's just like a brute force problem. Like it's similar to E in that like it just tells you what to do and you have to do it. It would be
K is DP, I remember. I'm forgetting.
Hmm.
Oh, yeah. Oh, no. K is not DP. K is math. K is well, you solve it using DP, but it's so the problem is given. So I've seen different versions of this problem. One of them is you can throw, let's say, some glassing from a certain level of floor. So if it's too high, it breaks. So if it's too low, then you know it can withhold that. So then you can repeatedly test it. So long as it doesn't break, it doesn't make it weaker. So the question is, if you are given multiple, then what is the optimal minimum number of experiments you have to run in the worst case? So if you have only one, then the only way for you to do is to start from the lowest and go up. And then the moment you break, you know where it is. If you start anywhere else, when it breaks, you don't know whether it's that one or it's actually some lower level. But when you have two, then you can start from some level, so that if that thing break, then you have to scan the value less than it. So then so that gives you the worst case of if it breaks, then you go to one branch, and then the worst case is anything below that. So I think if you have it's essentially triangular number, I remember. So if you have two, I guess you start at level 3. If it, well, I guess yeah. But you, when you compute this, you can just compute it using dynamic programming. So how many the state will include? Is this the one that do 5-dimension state that they mentioned? No,
I don't
not
think
this problem. Not
okay,
this.
okay, I think I understand how to do it
Yeah.
now. So,
Yeah.
like, so we have a problem, and the only like parameters are n and m. So I think what you do is you iterate over all possible like points to try the experiment on. And then there's two possibilities. So you can't control which possibility it is, but like if it doesn't break, then you have, so if it doesn't break, then you should only consider these floors. So it actually reduces to the problem of like n minus I. Maybe I'm off by 1, but I'll just ignore that. And then since it doesn't break, you still have m. And in this case, it reduces to I minus 1 because it broke. And n minus 1, you don't have that one anymore. So it always reduces to subproblems with smaller parameters. So if you define like dp of nm is the minimum in worst case, then you would take the best possible point I, and then for each one you evaluate it by taking the maximum of these two dp states.
Yeah.
Does that meet the complexity?
Yeah.
It'd be like n squared m.
Yeah.
I think that would pass.
5 seconds. Yeah.
All right. So yeah, I guess Trung, you want to take care of the rest?
Yeah, sure.
Hi.
Oh wait.
Okay, cool. Let's see. Share screen. Okay. All right, can you see this?
Yes.
Okay. I solved, I think BCD. BCD, ABCD, and I also solved Sudoku. Okay, so I'll talk about Sudoku first. Okay. So this is like the standard Sudoku, and they give you the Sudoku board and they want you to solve it. However, you are only supposed to use like two like deduction rule. The first one is the single value rule, like you search for squares that only have one possible value to put there, and unique location. In each important range, such as row, column, or subgrid, you search for a value that can be placed in only in one of the 9 locations. So yeah. So for this problem, it's just really brute force. It's like basically you loop as many times as you can. For each loop, you want to try using single value rule on every square and the unique location rule on any range, and that's it. So because like the size of the Sudoku grid is not too large, you can reasonably like enter the end state in a reasonable amount of time, and then just output the solution. If you can solve everything, then it's easy. If you cannot solve everything using these 2 rules, then it's not easy. Yeah. So that's just like a very straightforward first problem.
Yeah, so, I want to add a few things. One is I think one of the coaches said he implemented and then he tried it on New York Times Sudoku and realized the easy one there can be solved with these 2 rules. And then he had another heuristic. He add that, then that can solve all the hard ones.
Okay, I see.
And also, what could be the pitfall? So
I don't think there's any pitfall. It's just implementing these 2 rules as exact as you can. I mean, I think like interpreting these rules and then implementing it can be a challenge, but as long as you nail those 2 implementation down, it's just game over.
So it's I guess the other team had a lot of trouble with this problem. I guess it's
I see.
Could be just like
maybe it could be like forgetting one of the rules, like each rule is kind of encompasses multiple sub rules, like there's rows and columns and subgrids, so it might be easy to forget, like
or even variable name.
Forget unique location rule on only the subgrids or something. I don't know.
Yeah, it's pretty lengthy actually to code out all of the rules.
Again, this is, I guess, ECNA style problem. So it's about the sum games, and you pretty much do exhaustive search.
Yeah,
it's
like in this case, they even give you like the
rules to
the rule.
Yeah.
Okay, let's talk about Kinky word search. So they give you like a word grid, and basically they also give you like the word, and you want to search this word from in this word grid. So the word search game here is extended, so you can travel in any direction, forward, backward, diagonal in any direction, left, right, and you can like repeat words. You can repeat searching over places that you have already searched. For example, they said that you can find C++ here by going in the top right corner, C here, and then do a cycle on the plus here. Okay, so they defined, like, for a search pattern, they defined its kink to be the number of times you need to change your direction. Like, you need to change where you are heading towards, and you want to find if there's a way to search the word from this grid such that it has this exact number of kinks. Okay, so the grid is pretty small, 10 by 10, and the size of the string is also pretty small, like 100. So I immediately came up with the idea of having a DP where I define DP I J C and K. This means that can I for somehow standing at IJ having cleared C first, like having searched C first letters from the word already, and the current kinks that I have is K. Also, you would want to store like another variable for the direction you're heading towards. So I will have like a direction here too. So it's really just like a 5D DP. You can actually do a DFS on this. I did that instead of doing like normal bottom up DP. I think it's a bit more tricky to do, but either way, using this DP, you could just calculate the answer. The answer is yes when there is some position ij such that, and some direction such that DP ij, the number of letters and the amount of kinks that they give, there's exists one such position where it is true. I mean, one such state where it is true. Yeah. So this is just B.
So looks like you like kind of state search more than DP, because there are quite over the several weeks there are several problems there. You use Dijkstra or in this case just DFS.
Yeah. Okay. Let's talk about A. This is the greatest problem of all time. They give you the family tree. They give you like each person, they have this amount of children, and it's given that the parent-children relationship forms a tree, and they will give you they'll give you some queries. Each query they give you 2 people, and they want you to form their relationship. Grandchild, great-grandchild, siblings, 0 cousins, 1 time removed, or something like that. It's very straightforward, actually. You just build the tree and you read this whole definition thing. They explicitly ask you to find, like, for 2 people, what is the common ancestor that they both have that is as close to they are. So it's you can say it's an LCA problem kind of type, but the number of nodes on the tree is at most 100. So you don't technically have to code LCA. You just loop through all of the nodes and check if it's an ancestor and it is as close to both as possible. And then what if you have the LCA, then just read this part and then implement exactly what they want you to do. It's really weird. I guess the greatest pitfall of this problem is to implement the exact English English grammar rule. As you can see in my code, I'll just show my code here. All in the family. Yes. Incredible. Yeah.
Okay.
I hope in like world finals we don't have to like analyze other people's languages to solve the problems.
Okay, so there might be one other pitfall that is for especially for relationships of type 1, you would want the exact order, like B is the child of A. The others, you have A and B are siblings and A and B are cousins, whatever. So you can keep the original order, but for this exact relationship, you need them to be in the correct order. So there might be some case working to swap the variables around. Yeah. But yeah, that's A. Beautiful problem, I would say. Okay, cool. Let's move on with C. For C, they give you like some people that joins a trading community, and each person has an item that they have and an item that they want. Okay, so they define like a trading line to be some people, some set of people, some list of people, A1, A2, A3, A4, and so on, and AK, such that A1 has the item that A2 wants, A2 has the item that A3 wants, A3 has the item that A4 wants, and so on. AK minus 1 has the item that AK wants, and AK has the item that A1 wants. So if you build like the relationship graph, it's kind of like this. A1 wants has the item that A2 wants, who has the item that A3 wants, who blah 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 blah, AK, and AK has the item that A1 wants. So it forms a cycle. This is called a trading line. And you want to find the longest trading line in this graph. I mean, in this trading community, not in this graph. But we'll soon need to convert this into graphing. So the so the hard part of this problem is to read the condition. Okay, what's the condition? The condition is that no object will be wanted by more than one person and owned by more than one person. Cool. So we know that this is a functional graph. If we plot for person A1, we know that there's only one other person A2, at most one other person A2 connects to him, and at most one other person for a person U, we know that there's at most a person V that connects to them, and there's at most a person Q that U connects to because of this condition. Cool, so it's a functional graph. So we can just DFS on it and find the cycle.
So is this actually even a special case of functional graph? I guess functional graph is there's a out degree is 1, right? So you can only go to 1. So
yes.
Here also in degree is 1. So it's a special case. It's like what you have with the permutations.
I would say it's what is it called? What did I use? It's
functional graph. I just said in general. I think functional graph definition is out degree is at most 1.
It's 1. Yeah.
So here the in degree is also 1. So it's even more specialized.
It's much easier. Yeah.
It's so basically this kind of, but I guess this is similar to what you get in permutations. If you have a permutation, you have the same structure. So this graph, they have the structure where it's basically formed by multiple cycles. So
I think you can have paths too, because it doesn't guarantee like every item appears once and someone has it and someone wants it.
Does it not guarantee that if they can appear, if each one at most once, or so does that mean they has to be exactly once?
No. It can be 0. The first test case also has that.
Oh, okay.
Yeah. So candlestick is wanted by only 1.
I see. So there could be more things than persons.
Yes. But it really doesn't matter. Matter. You can just DFS on it. Yeah. Very cool. Yeah. So as always, there's some weird output where you can you can just output 0, but they decided to go fancy and says that no trace possible. But yeah.
ECNA always they demand the particular output.
Yes.
To be in output format.
Okay. All right. So I think this is the most interesting problem that I've solved. D. Okay. So it's a bit difficult. I don't know if it's a bit difficult to
it is. I guess at least it's something I look at it and couldn't figure out.
I mean, just to state the problem, it's a bit lengthy and a pretty detailed pack. But okay, so you have like two card lines. The first line is A. The first card line is called A, and the second card line is B. These card lines basically what do? They basically supply materials for the train tracks. So in the middle, there's some trains, some train cars. Cool. So they give you that each of the card in each of the line has like a resource value, like AI. It means that it can supply these many resources. Same with BI. BI is one, and so on. Also, these trains has capacity. It has a capacity that it's how much it can fill its resource to. So you can do the following operations. You can choose the first card of line A, fill like pour all of the resources, move all of the resources from this first track into from this first card into the first train car, as long as it doesn't like overflow the capacity. And then we rotate this card back and then fill it up to its resource capacity again. Same thing, there's another operation where on B, where you can move all of the resources from this train card, from this card into the train car, providing that it doesn't overflow. And then you move this card back in the line, and then you refill it up to its original capacity. So for more, I guess, elaboration, you can just look at the sample cases. Okay. And they and the thing is, if a train car it's filled to its capacity, then we don't need to fill that anymore because it's filled. So you can just remove it. You can just pop it from the top of the train, and the next train car will go on to be the top. So what they are asking is if you can basically fill all of the train cars to its maximum. Cool. So let's talk about a constraint a bit. Constraint of A, size of A is about, how many is that? 50? 50. Size of B is 50. AI is about 200. Still same with BI. Capacity of the car, however, of the train car is 2 million. And the number of train cars, we denote this as N. Let's just hold with train. Is 100. Okay. Let's just keep these details in mind. Okay. So a very intuitive approach is to do some DP. Because we can basically imagine A as a circular array. So the information we need to store from array A is the index of the first card. Similarly, because we can treat B as the circular array, we can just store like the state of B as the index of its first card. Cool. So I came up with this very intuitive DP. Oh my God, why is it so small? There we go, much better. So DP A index B index and car left. This DP says returns true if like at the moment I have the state, like the first train car that stays at A has index A int, the first train car that stays at B has index B int, and then the amount of train cars left is car left. Cool. So this also gives me exactly what is the car that I need to fill right now. Okay, so I use this DP and I figured out that this DP has like some transitions. There's a lot of transitions. So you can actually, because it's a circular array, you can, how would I say it? You can transition A int into A new int, where the new int is whichever index you want to be the next starting point, and B new int, where whichever index you want to be the next starting point. And you want to check if you can use some amount of material that starts at A index, ends at B, A new index, and that's from train card A, some amount of material that start at B index and at B new index at train card B's, like line B. And you want to know if it can fill up like the exact amount that is required by the current train card that we're trying to fill. Yeah. So up until this point, does it make sense?
Yeah.
Okay, cool. All right. So let's see. Let's analyze this for a bit. What we have here is A int A int, and what we have here is A new int. We realize that because we can go like this, and then we can just loop the circular array some few times. The amount that the amount of material that we can get from the train line A will be like whatever material there is between A int and A new int. Oh my God, my handwriting is a bit bad. So whatever material we have between A int and A new int plus X times the total amount of material on the whole train line A. That is because this total, we can loop it sometimes, right? Because it's a circular array. And this X is a variable. It's just whatever you can input in from 0 to infinity. It's an integer. It's a non-negative integer. Same deal with B. The amount of material you can supply from B will be material on B. I should have distinguished these variable names. Material from B, B int, B new int, plus Y times total B. And you would want these two to add up to equals to whatever capacity you're trying to fill. Okay, so let's do some quick maths. We move this part to the other side. So it's minus now. We move this part, the new material, to the other side. So what we have left is X times totals A plus Y times total B equals to capacity minus these two things, which I would call C. Yeah, I'll just replace it with C just for ease. So now we have a Diophantine equation, X times something, A times X plus B times Y equals to C, and we need to solve for to find some non-negative solutions of X and Y. So yeah, we can definitely do this. Cool. Yeah. So, however, let's optimize. Let's look at the complexity for a bit. There are like size of A times size of B times size of train states, and for each of these states, you also have size of A times size of B transitions. So this actually equates to about 6.25 times 10 to the 8. And if we have this Diophantine check, like this Diophantine equation solver, incorporated into our DP, then we actually need to have a times log here, because the solution, like the complexity of that is log, and we need to check it for each transition state. So it's a lot times log, which is not good. So what can we do? We realize that total A is a constant amount. Wow. Total B is a constant amount. Also wow. And C is a value that does not exceed 2 million. So we pre-compute all of these C's and check if they are computable. And then we can just use this pre-computed array to replace our log here. So yeah, that's the complexity. That's all of these problems. That's the whole of this problem.
Okay. I see. Yeah. So
Yep.
just to recap, to use knapsack DP to figure out using the total of A, total and B, how much of this under 2 million can be filled. Then you compute your DP state transition by lookup from a particular position of A and B for another particular the difference. The difference contributed from here and whether the remaining amount can be filled using the total amount.
Yeah. Or actually, for pre-computing, I don't like really do knapsack. I just do like a direct Diophantine check. So it would be 2 million times log, which is fine.
But knapsack should work too, right?
Yeah, I think knapsack should work.
Okay.
It would be only like 2 million times 200, so that's fine.
Oh. Okay.
Yeah. So
why time 200? What's the word?
Oh wait, does it need 200? I don't think it needs 200. Yeah.
Yeah, it's really just the 2 million array filling.
Oops, I think I write too many code. More code than I needed. Okay. Anyway, yeah, that's this problem.
Okay, cool.
All right. That's actually what I have to share.
All right. So does anyone have any questions? Either Patrick, do you have questions? No?
No.
Okay, good.
No.
Yeah.
Okay.
Congratulations, Riley and Trung. Very good job.
Yeah. Okay, I'm stopping.